I would like to call Professor Gerard Hooft for his talk.
Thank you very much.
It's on. It's on.
Thank you very much. Can you hear me?
Yes.
Okay, I have to apologize to half of the audience if my talk gets too technical. I also have to apologize to the other half of the audience if I'm not putting in enough technical details. Anyway, you may have noticed that in the program of this meeting, several talks, even plenary talks, contain the words conformal symmetry and the words scaling in their title. And this indicates that perhaps something is happening with the way we think about symmetries in nature. And I tend to believe that conformal symmetry will become as essential a symmetry in nature as special and general coordinate transformations will be. So it is going to be a phase transition in our thinking, perhaps. We don't know in which direction theory is heading, but this is just a message that I want to convey to you, that there is perhaps something interesting happening in our understanding today. It seems to be clear that the way we understand black holes today is not enough. It is not enough if you want to understand the quantum properties of a black hole. We need to add more different theoretical understanding to what we have today. And the theoretical understanding that is missing seems to be the question how to include conformal symmetry in our description of space and time, in particular when we want to address the questions concerning the Planckian regime. The Planckian regime is the region in space and time where things become extremely small, so small that also gravitational effects together with quantum effects and relativistic effects all at the same time become equally important. So the idea would be that conformal symmetry is not just a mathematical curiosity, an approximate symmetry of nature that will be broken to some extent, because we all know that ordinary phenomena in the universe do depend very much on scale. All atoms have a given size, and they have a given decay, lifetime, and so on. So lifetimes and sizes are important in nature. They have absolute significance, not relative significance. Yet, in spite of this, there may be something very essential going on, the scale transformations. So the ingredients of the new theory would be local conformal invariance. Well, the theoretical part of that is very well understood, so I put 2 pluses behind that. But the other problems that are going to be associated with that is problems with indefinite metric fields. And this we do not understand so well. I put a minus there. And then there's a question about quantum mechanics. Normally, we think of quantum mechanics as an absolutely necessary fundamental framework in terms of which we have to formulate all theories of nature. The question whether you can put an end to that, whether you can actually replace quantum mechanics by something that restores classical logic to our way of thinking, that has been very strongly opposed to. The entire 20th century was science was in the absolute conviction that quantum mechanics is a fundamental change of our way we think about experiments, we think about physics, we think about laws. and to try to turn that back is something like a blasphemy, but I think that eventually we have to think in more general terms when we try to formulate laws at the Planck scale. Anyway, one of the basic difficulties in our understanding is black holes, and the problem is usually framed in terms of the question of information. What happens with information going into the black hole, and what happens when a black hole radiates out particles, which it can do according to the laws of quantum mechanics in principle. Then these particles coming out of a black hole also carry information in them. How can that information be related to the information going in? Or more precisely, a black hole should be described eventually as an object which is as quantum mechanical as everything else in this universe. We like to describe the black hole as being in terms of quantum states. We want to understand how those quantum states can be rephrased and understood in terms of the vacuum fluctuations. You see, the Hawking particles that are being emitted by a black hole are emitted because we know that the vacuum near the horizon of a black hole undergoes vacuum fluctuations. Now, these fluctuations are, in terms of quantum mechanics, you know exactly how to describe them in principle, but how they can turn into real physical particles is still something of a mystery. And I think present theory does not properly address these things. It has to do with the presence, of course, as I said, the horizon surrounding a black hole, but also the singularity inside a black hole may have something to do with this, and we want to understand that. There has been rather recently, last decade or so, questions about the so-called firewall, as if the horizon of a black hole is not transparent to observers going in, but somehow observers trying to enter into a black hole will be killed by the Hawking particles. That has been an idea that has been floating around, and again, to my mind, that means that we have not understood something about the theoretical description here. And I'll explain to you how I think all this has to do with this conformal symmetry being a more fundamental symmetry of nature than one might think. For instance, if you compare two observers, one observer going into a black hole and the other observer staying outside, then the observer who goes into the black hole goes into a black hole with a specific value of its mass. The mass of a black hole is very large. Think of an astronomical black hole. Observer entering a black hole which is astronomical in size. That observer still has a couple of seconds or minutes or even years to live before he's being killed by the singularity. What happens to that black hole and to that observer? And that observer will see a black hole with a definite amount of mass, capital M. However, someone watching that black hole from a great distance, the distant observer, also sees a very heavy black hole, but that observer sees the black hole slowly shrink. That's because the black hole emits Hawking particles. Well, in the real universe, the black hole will usually absorb much more things than it can possibly emit, because the quantum particles a black hole emits are very, very low energy and very tenuous radiation. It takes many times the age of the universe for such a black hole to decay. But now let's ask a more fundamental question, and as theoreticians we ask these fundamental questions. What if? So what if we allow that black hole to decay and disappear altogether? Well, it disappears the moment that this ingoing observer still sits at the horizon. You never see, from a distance, you never see an observer going through the horizon. You see it, that the observer stops. So do we see that observer actually shrink? What's happening here? And there's something incomplete in our understanding here. Does the observer see the black hole mass shrink to zero, or does it stay constant? Who is right? Now here comes the notion of black hole complementarity. It was introduced a couple of decades ago in various discussions among physicists, among myself, Leonard Susskind, and other people. And black hole complementarity says that somehow an observer going into a black hole, an observer staying outside, they are describing the same thing. So whatever your ingoing observer sees and describes, with a proper dictionary, it can be translated into what an observer outside sees, and how that observer sees the states of the black hole evolve and eventually change, and describe these things in terms of rigorous physics. The problem is they can't be both right, not according to standard theory. So the idea is, in theory, we should change standard theory, we should add something to it. We are not going to throw things away. We're not going to say that standard theory is wrong. No, we're saying it's incomplete. Just like Newton's theory is not wrong, but as Einstein showed, it was incomplete. You could add something more to it. Similarly here, if we add conformal symmetry to our description of black hole, we might get something better. And something better would be that both observers have it right. They both see and are able to describe how things evolve. But when they say that the other one is lying, they're wrong. There should be a translation, a dictionary from one to the other. That's what black hole complementarity is trying to say. Now, when I talk about conformal symmetry, actually the easy part of it is to describe what you really, or the beginning of the theory. The beginning is what you really should start doing. And the beginning is that the thing we call a metric tensor, the object that describes sizes of things and timescales and such, that object we call G sub mu nu of space and time, that thing is not unique. It is rather easy to say that one observer sees a metric tensor G mu nu, another observer sees a metric tensor G mu nu multiplied by a constant coefficient, which I call here omega squared. So the square of omega, yeah, you can see this here, is the so-called conformal factor. And now it could be that two observers disagree about the conformal factor. The nice thing about this is that this disagreement would be rather easy to incorporate in a theory. In fact, previously, already in the 70s, it was clear that when you renormalize or try to renormalize quantum gravity, the first thing you discover is that you have to make field redefinitions. And that includes the energy momentum, the metric tensor field. The metric tensor field gets renormalized, and the renormalization goes by adding pieces of the curvature tensor to the metric tensor. That was considered a blasphemy by general relativists in those days. In the early days, when I mentioned this, I got, in fact, a meeting like this, I think it was the third Marshall-Grossman meeting, where I mentioned this in a talk, that the metric tensor is not absolute. You should add the pieces of the curvature tensor to it. The people started to shout and say, that's wrong, you know, metric tensor is fundamental. But it can't be if it's quantum mechanics. But the way we often change then the metric tensor is to change it completely. That is very dangerous in a theory to do, because that would modify the location of the light cones. So whatever you do to a theory of the energy momentum tensor, or sorry, of the metric tensor, you should be very much aware that you're also changing the location of the light cones. And this is dangerous, because then you change the causal order of events. If 2 points lie inside the light cone for one observer and outside the light cone for another observer, then the question is, what's the causal relation between these two events? What's the causal structure of your theory? It's dangerous to tamper with the causal structure of a theory, and that's why the first thing to think about is multiply an entire metric tensor with a factor. That's easy, because that does not affect the location of the light cones. They remain where they are, and so the causal order of events stays the same. But if you change everything about the metric tensor, then you also change the causal order, and then you are seriously damaging the theory. So this is why we just consider multiplying the metric tensor with a constant. Then I define a new g hat and an omega. Split things up. G hat is the metric tensor modulo its conformal parts. If you do this, then there's a very simple transformation where you say I multiply g hat with a function omega squared, and I divide omega with by the same factor omega. Of course, nothing changes. So if in today's theory of nature we make this substitution, that what we call metric tensor today is omega squared times a new metric tensor, then this is a very trivial invariance. So trivial that you could ask, why is this useful at all? What's non-trivial about it? Well, it becomes non-trivial precisely when you look at the horizon of a black hole and different observers have different ideas about what the vacuum state is. The point is, this omega has a vacuum excitation value, which would normally normalize to 1 or 1 over 8 pi Newton's constant, depending on your notation, but you normalize it to a fixed value. And you say that value is the vacuum excitation value. And now I say, but an ingoing observer, an outside observer, they disagree about what the vacuum state is. They both thought the vacuum state is a state of lowest energy. But definition of energy for one observer is not the same thing as definition of an energy by another observer, and that's why they disagree about the vacuum state, and so they disagree about vacuum excitation value, and therefore they disagree about this coefficient omega. And that's how this can go in and become something non-trivial. So think now of a curtain. The curtain actually is a shower of Hawking particles leaving a black hole. And think of atoms at this side of the curvature of the curtain and atoms at the other side of the curtain. They differ in size. That's very strange and very unorthodox. If two observers disagree about coefficient omega, do they disagree about the sizes of atoms? Well, the whole point is that matter density inside a black hole becomes so great that atoms can't live by themselves anymore. So you can't define what an atom actually is. So disagreeing about the size of atoms is not so strange as it might sound, because of the density of matter there. When there's very dense Hawking radiation, you don't know anymore what the vacuum is, and now you are becoming uncertain about what the size of atoms is. So this is how this comes about. So there are theta jumps, actually not in the value of omega, but rather in the gradients of omega. There are theta jumps which cause this strange looking effect. Now, the mass of a black hole, and this is central of the whole idea, is not conformally invariant. Masses, of course, are not invariant under scale transformations. They become bigger or smaller. And that's the notion of black hole complementarity. So the black hole metric is, so this is just the technical part. This is the familiar Schwarzschild solution, but you can rewrite it by saying that I put the mass square of the black hole just in front of everything, and let that thing now depend on time. The question is, does it depend yes or no on time? Is a black hole where you ignore Hawking radiation, and if you have no matter going in, its mass will remain constant. So then m squared is time independent. But for the observer who waits long enough, he sees the black hole shrink, and a black hole depends on t, or rather t tilde, which is retarded time. So the factor m squared depending on retarded time is the amount of disagreement between the ingoing observer and the outside observer. And the outside observer, of course, sees no horizon and no singularity, but the ingoing observer does. And that's also an important difference between the two observers. In such a theory, you might make a transition from the standard picture of a black hole, which is more like this. In a standard picture of a black hole, you have particles going in, producing a black hole and producing a singularity. And then here, before the particles are going in, already a horizon opens up. And the horizon stays there, and Hawking particles are just an afterthought. You do quantum field theory in the vicinity of a black hole, you see a couple of particles coming out. But in a new theory, this picture might become more symmetric. You have the ingoing particles like this, the outgoing particles like this, and I treat them in a time reversal symmetric way. This is another important ingredient of theory that was missing here, the notion of time reversal invariance. Can we regard Hawking particles as being as classical as the ingoing particles which make a black hole? In ordinary physics, no, but in the future theory, perhaps yes. The Hawking particles are just as physical as the ingoing particles, so we should describe the black hole in an in-out symmetric way, a time reversal symmetric way. And then you get something looking like this picture. Not quite, because the theory is complicated, and so the internal region, in a sense, doesn't exist. And actually, what conformal symmetry can do is change the black hole, which forms and decays at the same time, into a picture which looks roughly like this. In this picture, you see the ingoing particles, and then you see the outgoing particles here, and inside you see, well, a very strongly peaked Ricci scalar curvature, but no singularity, and no horizon even. The black hole becomes topologically trivial. When you say such a thing, the first thing you ask is, why did we not say this 50 years ago? What's wrong with this theory? Why did people not believe this? And why do many people here still not believe this? The reason is something very, very unnatural seems to be happening. The imploding matter making a black hole is not ordinary matter, but it's dynamite, together with the fuse. You make a black hole out of ingoing matter, but just before the ingoing matter reaches the horizon, or practically at the same moment it reaches the horizon, the fuse goes off and the matter explodes. The explosion is so strong that it generates a gigantic amount of Ricci scalar curvature. And then the outgoing particles, which are a gigantic cloud of degrees of the explosion, are being redshifted so much because they are so close to the horizon that they turn to Hawking particles. This picture would replace the conventional black hole picture into a picture where you have no horizon and even no singularity. This is just a regular region of space-time. But to get the picture right, you need conformal transformations. Why? Well, the standard textbook would not even contain this description of a black hole because it would be very strongly criticized. The criticism would be, yes, how did the fuse know at which moment to explode? And that's, of course, crazy. So in ordinary physics, this picture is totally crazy. The ingoing matter explodes exactly at the right moment. How did it know? Well, the remarkable thing is that the ingoing observer doesn't see that explosion. The ingoing observer sees ingoing matter continuing inwards to make a singularity. But the outside observer sees the explosion. How can this be? They are both right because one is a conformal transformation of the other. If we knew how to perform this conformal transformation, we could say both observers are right. The external observer thinks that the matter is exploding here. The ingoing observer sees nothing of the sort and sees matter continuing its way inwards. To do this right, we need to modify the theory. So when you're criticizing this, please be my guest and start yelling. But remember that to get this picture right, you do need to modify the theory. Normally speaking, it is not right. It would, however, turn a black hole into a totally regular soliton-like object, very much comparable to magnetic monopoles in the electroweak theory. You remember in the electroweak theory, in the old theories of electromagnetism, Paul Dirac had proposed how to describe magnetic charges. But his magnetic monopoles were singular. There was a singular Dirac string, you remember, leaving the magnetic monopoles. But Dirac discovered that nevertheless these magnetic monopoles could behave like freely moving charges. And that was a superb piece of work, but he couldn't do it without having a singularity, and in his theory he could not compute the mass of a magnetic monopole. Now in electroweak theory we discovered that actually you can make regular solitons out of magnetic monopoles without Dirac strings attached to them, but they are just a peculiar combination or construction of the Higgs fields and the Young-Mills fields, which together constitute the theory of electromagnetism in combination with other particles. So now I claim the black hole that we normally consider as something topologically distinct from ordinary matter now becomes identical to ordinary matter. It becomes a soliton. And this is what I do think a future theory of gravity should be heading to. So in this respect then, our theory of gravity is going to look more like the standard model of elementary particles. Remember, the standard model of elementary particles was a superb result from the 20th century physics, that now we understand how to describe particles in great detail. We could only wish and dream that we could get something like this for quantum gravity. But this is what we all try to do. Now here is where my talk becomes a bit technical. One should consider gravity together with matter. And then say, well, gravity itself may have this conformal symmetry built in. the omega field is one of the dynamical fields of gravity. No sweat there. But when you put in matter, things seem to be more problematic. So what happens with the matter Lagrangian, which is the ordinary Einstein-Hilbert part plus the matter part, which may contain a Yang-Mills part, a bosonic part, and a fermionic part. What happens to that when you make this substitution? Well, that part of the theory is easy to answer because we can do that calculation. And we can also ask what happens with this trivial-looking conformal symmetry. Well, this omega field then re-emerges this way. And actually, this is the reason why I wrote omega squared. If you write omega squared in the substitution originally, then the action in terms of the omega field becomes just as if the omega field is an ordinary scalar field in the system. Other scalar fields like phi, like the Higgs field, contain kinetic parts very similar to this, and then it contains self-interactions. The self-interactions just look like the cosmological term for the omega field that also produces an omega to the fourth interaction. And you find the entire thing is entirely conformally invariant. It looks like renormalizable also. It looks like a renormalizable interaction, and it looks like a conformally invariant interaction. So this looks perfect except for one little thing. The kinetic term for the metric tensor field has disappeared. G hat has no kinetic term. The kinetic term now sits here, but now it plays a role as a kinetic term for this omega field, but not the rest of the metric tensor. That is why there's still something wrong in this theory. If the G hat has no properly behaving kinetic part, then we can't do the usual tricks we play when, for instance, when we act with the standard model. Now, you can write the field equations if you have no kinetic part for G hat, but then the field equation becomes something rather extraordinary. They really say that the total energy momentum tensor of the theory should vanish. That's because if there is no kinetic term that depends on G hat, then variation with respect to G hat should give something that cancels all together. And that variation just gives the energy momentum tensor, T mu nu total, which is T mu nu of matter minus the T mu nu of the omega field, because that is now added to the thing. The minus sign comes about because there's a difference here. There's a minus signs here and plus signs here. So the sign of the omega field is wrong from conventional viewpoint. That's why there's a minus sign. And then you say total T mu nu is T mu nu matter minus T mu nu of the omega field that vanishes. Actually, this is just Einstein's equations. T mu nu matter minus the G mu nu field, Einstein field, together vanishes. Of course, I did not change the theory. I only changed the mathematics of the theory at this level. So, nothing has been solved yet. We still have the quartically divergent terms generated when you have the gravitational field forming, looking at closed loops with the quantum corrections. These are the familiar diagrams that were already being studied in the 1970s to discover that gravity is a very divergent theory. It cannot be renormalized unless you say that these terms will search for a counter term. Well, if you phrase the theory this way, the counter term should become conformally invariant. And there is only one conformally invariant combination of the curvature fields, which is the square of the so-called Weyl curvature. If you don't know what Weyl curvature is, I can't explain it here. If you do know, then you know that this is a conformally invariant component of the curvature field, and that's the only term that may have to be added to the theory. So if we add that to the theory, we get the ordinary renormalizable looking theory. And in fact, indeed, according to the standard rule, such a theory will become entirely renormalizable. If we accept such an extra term in Lagrangian, this would change everything. This term is normally not present in quantum gravity. If we add such a term, the theory becomes renormalizable. The one overlap that term would be the usual perturbation expansion. The difference between this theory and the standard theory, however, is a more subtle one. If we use G hat instead of G mu nu to renormalize the theory, everything changes. Why? Well, G hat defines the sizes of things differently, and now when you renormalize a theory, you have to say that at very high energies, a subtraction has to be made. But what is very high energy? Well, according to observer uses G hat rather than G, very high energy means something different. And that's why the renormalization procedure becomes totally different if you apply it in this theory. In fact, without this modification G hat, you would get 1 over omega terms. But if omega is an ordinary scalar field theory, scalar field, then 1 over omega terms should be forbidden. So I had big discussions about this with just even a week ago about this problem, what to do with these 1 over omega terms, because normally you get them, but now somehow they have to disappear. The omega field is an ordinary scalar field. It should not become singular when the field goes to 0. And that's a very peculiar situation. So, I don't have so much time anymore, so I'll just briefly mention a few good things and bad things of the theory. The good thing here is that such a theory of gravity would seem to be renormalizable, but we're not out of the woods yet, as I will explain. Also, a good thing seems to be that this conformal symmetry doesn't work all by itself. It is associated with conformal anomalies. So we still have lots and lots of work to do. We have to rephrase the theory in such a way that the anomalies cancel out. This doesn't happen automatically. It only happens if the theory, which I had a few slides earlier, if that theory has all its parameters arranged in such a way that all the beta functions cancel. They become 0. Or in other words, which is more familiar to the particle physicists here, the theory has to be at a fixed point of its renormalization group transformations. So the beta functions must all vanish. What is good about this is that the beta functions vanish only in one point of the standard model, which means that everything should become computable. We have been grown up with the idea that parameters in a standard model are not computable. They are God-given. You have to determine by experiment. Well, in this theory, would no longer be the case. In this theory, all parameters of the standard model, and that includes all masses, it also includes the cosmological constant, they should all become computable. That's a great asset. That would make this theory fantastic. So far so good. But there's a problem here. There's one unknown feature, which is the algebra of the standard model. Today's standard model are based on algebra where this whole procedure doesn't work. And that's, of course, the bad news. In the standard model, as you know today, there is no fixed point in a physically acceptable domain. We can't compute the cosmological constant, or if you would try to compute the cosmological constant, you would get a very, very large number. And this is, of course, basically unacceptable. So, and that is because there is a problem which we have not solved. More bad news in this theory. We haven't understood the standard model algebra at all, because if you try to compute all those constants, they become all of order 1 at the Planck scale. This is totally wrong, and what's wrong about that is that the real world, as you know it, the universe, has a hierarchy problem. There are enormously different scales in this universe. There are very tiny numbers and very large numbers. No theory today, not even string theory, loop quantum gravity, you name it, no such theory can explain why there's very large numbers and very small numbers in our universe. So this is a big mystery, and it's very much present also in the theory I phrased here. We should try to find a good understanding, arguments as to where big numbers come from in our universe. And we have to keep this problem in mind while we are thinking about this theory. The worst piece of news about this theory, however, is that it's all wrong. Many people will reject it right away, and that is because this Weyl curvature square is not an acceptable kinetic term for the metric tensor. Why? Because it generates negative metrics. And in particular, it's very interesting to work it out, and I worked out the equations here to find out what kind of negative metric does the Weyl curvature square produce. The answer is very simple. If you just plug it in the way I just said now, what it does is it generates a spin 2 particle with negative metric. It has exactly 5 internal degrees of freedom. A spin 2 particle has 2L plus 1, which is 5 in case of L equals 2. So there are 5 components which have negative metric, the 5 spin components of a heavy spin 2 particle. Since the name was still lacking for this particle, I propose a name Gravitello. has nothing to do with the gravitino, so it's something else. It has to do with the gravity, of course. It's a heavy, massive companion of the graviton, which sits there spoiling everything because of its negative metric. So the question is, how do you deal with negative metric? And normally speaking, when you do that, if you have a theory with a negative sign in its propagator, it means that unitarity is violated. If you try to compute S times S dagger, and you want to prove that that must be the identity matrix, you have to sum over all intermediate states. If you have a minus sign in your propagator, such as for this gravitello field, then you have the light particles and the heavy particles contribute with the wrong sign. So the gravitello field has a negative, the gravitello particle has a negative probability for it to be produced. Well, its mass will be so heavy that no experiment can produce it at all today. But if it's being produced with negative probability, we have a problem. We can rephrase the difficulty. And I think my time is running short, but the rephrase the difficulty by saying that the, just 1 minute will be all right? Okay. That the sign of the harmonic oscillators, which these fields form, is the wrong sign. So there's a harmonic oscillator which is a mountain rather than a valley like here. So that means that the creation and annihilation operators had to be interchanged. We had to write down a bottom value for the total energy. That replaces, if you put a lower bound on those energy levels just to restore energy as a stable notion, then you remove states out of theory. Eventually you want to understand how at the Planck level, at the Planck domain, the number of total physical states is being reduced. You want to have a lower bound in those states. That turns quantum mechanics into deterministic quantum mechanics, because now the number of states is finite. That describes a deterministic thing going into a cycle. And this adds to the theory, the idea that quantum mechanics may become deterministic at the Planck scale. So that's why I started at the beginning of the lecture. At the very end, you see deterministic quantum mechanics may come back to restore the problem of indefinite metric in these fields. This would restore the metric problem, but not completely, only partly. It still generates incorrect mathematics in the whole scheme. So yes, unfortunately, I have to end here, and I'd like to proceed with private discussions as much as possible, but this is basically my message about how important conformal symmetry could possibly be, but there's so many problems still waiting for us to be solved. So I think we're heading for new exciting times in the not so distant future. Thank you.
Thank you very much.
So that's nothing's okay.
We have time for one very quick question, a very compelling one, please. Yes, there is one question there.
Where's the question?
Gerard, on one of your first transparencies, you mentioned that an observer falling in would see a black hole with essentially constant mass as one of the two statements introducing the contradiction in the firewall problem. But if you calculate the actual rate of photon emission by Hawking radiation, it's very rare. It's only 1 in, say, 5,000 light crossing times that a photon is actually emitted. In other words, practically speaking, the black hole mass is decreasing by small steps, as observed by an outside observer. Now, you would think that an inside observer would then also witness similar steps, except, of course, at much higher frequency, so that also an infalling observer does not see a fixed M, but an evolving M.
Okay, an observer falling into a black hole doesn't see the Hawking particles at all. So that observer thinks he's going through a perfect vacuum, including, of course, vacuum fluctuations, but those don't generate any particle in the optics of the ingoing observer. The outside observer sees all these Hawking particles. So there's a clash between what they observe. And I claim we have to take that clash more seriously than normally done. The standard picture is that either they both see particles or none of them sees the particles. But the idea that one observer sees particles where the other observer sees nothing is something we have to get used to. I'm sure this doesn't entirely answer your question, but that's the problem. We have not properly not really been able to formulate this theory in all its details. As long as we can't, Of course, my answer will not be satisfactory to you.
Actually witnessing
Oh, your
Hawking
microphone is not on.
I'm sorry? Is it on? I'm making a distinction between actually seeing a Hawking particle and actually witnessing what I think is a weaker condition, steps in the mass enclosed by the sphere on which the observer is falling in.
Well, imagine now a classical general relativistic experiment. For instance, when you have this, the left picture here, this picture here of the black hole, then the horizon already opens up here. An observer going in here will go, well, here sees the vacuum. According to standard laws of general relativity, this observer going in here sees nothing happening at this spot. How could he? That if he would see something happening, that would violate causality. This spot is totally empty space. So here definitely nothing happens. If an observer looks here, he just looks at these particles which are not existing, going through the other particles. Again, there's no reason for this observer to see anything happening according to the standard rules of general relativity, which we might question, of course.
It's very local. Yeah.
But in principle, according to standard general relativity, an ingoing observer going in along this line sees absolutely nothing out of the ordinary happening, and certainly doesn't see that the black hole suddenly disappears in front of his eyes. That's impossible. So I claim we should have a theory where both pictures are right. The outside observer sees a shrinking black hole, the ingoing observer doesn't see these particles, and therefore doesn't see any change in the space-time metric that would be caused by such particles. And that's the essential ingredient that we need to include in the theory, which wasn't there yet.
Okay, we have to stop here. This is a very interesting discussion, but we have to stop here because now we thank again Professor Hooft.